Let's look at other applications of Newton's laws. So we're considering the motion of an object falling in a fluid. We can consider two models. The first model is a case where the resistive force is proportional to the object's velocity. So in this case, let's consider that we have a fluid in a container that way, and we drop a ball or a marble, if you like, into this container. The weight of the marble is mg, and there's going to be a resistive force F subscript r pointing upwards, and let's say the ball falls with a velocity v, or the bead falls with a velocity v. We've said the resistive force is proportional to the velocity, and since it's opposite to the direction of motion, let's write it this way. So by applying second law, the net force on this bead is going to be equal to the mass times acceleration of the bead as it falls through the fluid. The net force, of course, is equal to the weight mg minus the resistive force B times V, and that should be equal to m times a. Since the object is falling in a fluid where the resistive force is proportional to the velocity, we can consider the motion of the object the following way. We consider that when we initially drop the object into the fluid, the object has initial velocity 0, and acceleration is just acceleration of gravity. As the object falls through the fluid, if the fluid is thick enough, the acceleration declines and goes to 0 as the velocity increases to a terminal velocity. So let's first describe the motion of the object in the fluid. We consider that the fluid is thick enough so that it slows the motion of the object as it falls in it. So the correct term to use is a viscous fluid. Instead of saying the fluid is thick enough, we can say the fluid is viscous. So in a viscous fluid, when the ball is initially dropped in the fluid, at the top of the fluid here, the ball will initially have a velocity equal to 0, and its acceleration will be equal to g. And as it falls in the fluid, its velocity would increase. Its velocity would slowly increase until it reaches a terminal velocity. And this velocity we shall call vt. That's our terminal velocity. So let's say v equals vt. And acceleration a equals 0. So the acceleration will decrease slowly as the object falls until the acceleration becomes equal to 0. So I'll just state what I've written above, that the object speed increases until it reaches a terminal velocity v subscript t, and at the same time the acceleration a, which is initially acceleration of gravity, decreases until it becomes 0 at terminal velocity. So with this in mind, we can say then that mg minus bv is equal to m dv dt, since acceleration is changing. So a is equal to the change in velocity with respect to time. So we can write m dv dt to be equal to mg minus bv, and we can remove the v's, so we have dv, we can remove m, so we have dv dt equals g minus b over m times v. So let's first say that at terminal speed v equals v subscript t dv dt, which is our acceleration, should be equal to 0. Therefore, we can say 0 is equal to g minus b over m times v subscript t. Therefore, we can say v subscript t times b is equal to mg. Therefore, the terminal speed v subscript t can be written as mg over b. This occurs when acceleration is equal to 0. Our equation dv dt equals g minus b over m times v is called a differential equation, and we will not go through solving this equation, but I will quote for you the solution. So our solution of this differential equation for v equal to 0 and t equal to 0 is satisfied when we have v equals mg over b, and in parentheses we have 1 minus e raised to the power minus bt over m, where we see that bt is equal to mg over b. Therefore, b can be written as b subscript t 1 minus e raised to the power minus bt over m. We can also make the substitution that the tau is equal to m over b, where tau is a time constant. Thus, we can write v equals v subscript t 1 minus e raised to the power minus t over tau. The time constant just means that when an object is released at t equal to 0, it reaches 63.2% of its terminal speed, v subscript t, when t is equal to tau. Okay, so note that this letter is a Greek letter called tau. The second model is a little bit different. Let's consider a model where the resistive force is proportional to the speed squared. So this is a similar scenario. This time you drop an object in a fluid again, and the object has a mass m, so its weight is mg, the resistive force is r, and the object is again falling with a speed v. The same situation applies. The object is going to start off initially at speed v equals 0. So we can say that, note that the motion proceeds the same way for this model also. This is an example of a skydiver jumping out of a plane. So let's start off by saying that the resistive force depends on the following factors. So we have already identified that this resistive force depends upon the constant d, which is the drag coefficient, the density of the fluid, the cross-sectional area of the object, and the speed squared. So d is drag coefficient, rho is fluid density, in this case the fluid is air, a is object cross-sectional area, and v is speed. So again, the net force on this object is equal to the weight mg minus the resistive force, and that should be equal to m times a, according to Newton's second law. So we can say that acceleration a, if we divide through by mass, a becomes equal to g minus d rho a divided by 2m, and then we're multiplying that by v squared this way. Terminal speed occurs when the gravitational force is balanced by the resistive force, i.e. when a is equal to 0. So with a equals 0, we shall say g is equal to d rho a over 2m times v squared terminal. So the terminal speed can be written as the square root of 2mg divided by d rho a. So this is the end of the examples for applications of Newton's law.